Welcome, everyone. It's great to have you here at the end of the day. Thank you for sticking around. We've seen some pretty exciting announcements today. I want to welcome back to the stage Urs Hölzle, who's the, as you already know, is the Senior VP in charge of technical infrastructure at Google, responsible for building all the data centers. And I also want to welcome Jeff Dean on stage. Many of you know Jeff, and if you don't, you probably should. He's a senior Google fellow and has had his hands really in every piece of major infrastructure at Google, and he's built many of the systems that you know and have heard about and have inspired many open source projects such as MapReduce, BigTable Spanner. He's worked on web search, the ad serving system, basically all the important bits at Google. So, Urs, if I can start with you, maybe ask you a couple of questions that are sort of on top of the developers' minds today. We've heard a lot about the commitment to cloud and everything that Google's putting behind the Google Cloud Platform. Can you maybe tell us a little bit why cloud is important to Google, why cloud is important to you?
Sure. So it's really two things coming together. One is that we always like to think about the long term. And if you think about it in a 10-year time frame, there isn't really any chance that 10 years from now, the public cloud isn't a major, major part sort of the world, right? Today, kind of everyone talks about it, but the reality is that all who are using cloud are part of sort of the vast minority of developers and IT folks who actually are doing it. Yeah. But if you think 10 years out, there's just no question that a reasonable fraction of the world's server-side cycles are going to be in the public cloud. And that's going to be an interesting business for us, for others too. Yeah. And so if you look at just the numbers, it's easily bigger than the advertising business is for us, right? So that's kind of the business opportunity side. And then the second part is really the technical opportunity. We've been living as Google in the cloud for 15 years, basically, right? For 13 of these 15 years, our cloud was just for our own use. But we've learned a lot, and many of the things we learned apply kind of directly to sort of the public cloud. And you mentioned Jeff, right? I mean, we came up with MapReduce, and that's now turned into sort of a common thing that everyone uses. It's just that we had the problems earlier, and that's why we kind of came across the early. So there's a big opportunity for us to actually take that technical leadership and really turn it into product leadership on the external side, just not just on the internal one.
Okay. So yesterday there was an article in Wired magazine where you were quite prominently featured, and in that article there was a memo that was described that you wrote to folks in your organization, to the technical infrastructure team, but also to the rest of Google, and you set a call to change in direction in motion. Can you maybe talk about what you wrote and what was the reason for sending this memo?
Sure. Yeah, that's engineers get to write code, and managers get to write memos. So, we compete on equal footing.
No, how many lines of memos have you done this year?
That's right. My memos are very concise, and I write them in Emacs. So, I write them in Google Docs, of course. So we're really going through a change. So we started about 2 years ago to redo our internal infrastructure, because in the 15 years that we've been doing it, we learned a lot. And we went through a big push to simplify things, right? We accumulated a lot of stuff because we tried a lot of things, and some of them worked and some of them didn't. And now we think we actually know pretty well how to do that. And we're using this infrastructure to power cloud, and we want those two to be the same. And previously, so the last 2 years, was really the preparation for that, laying the groundwork. And now that platform compute engine is actually live, no longer beta, now it's time to really move many more of our infrastructure systems onto the external platform. So the New World memo that I wrote was really about taking this year and making this the #1 priority for everyone, and have really the majority of the organization work on the external product rather than the internal one. And one of the reasons we can do that is because our internal one is actually in pretty good shape. So, not working just, quite as much on it is not going to hurt anyone. Right? And so this year we're really spending the majority of our effort in externalizing the many things that we haven't externalized yet, because the platform now is ready. And so now adding people will actually make things go faster rather than slower.
So it's a pretty significant shift.
Yeah, definitely.
Hence the memo.
Yeah, yes.
So App Engine in less than 2 weeks' time turns 6. So Google's been working on the cloud platform for quite some time, but it seems that not only seems that there's actual accelerated launches that have been happening in the last 12 months, and of course with today's event. Was delivering and creating the Google Cloud Platform always the plan for you from day one, or is this something that has evolved over time?
So I think the dichotomy between infrastructure as a service and platform as a service is really a kind of a false dichotomy. It's really much more of a grayscale, and you saw that today. We kind of want to make it a grayscale where you can be all the way over here, where we make all the choices for you, and your life is really, really easy, or over here where you can make all the choices, and your life is really, really flexible, but maybe you have to do a little bit more work. And there aren't just these 2 points, but there's basically anything in between. And so I think what we realized was that even though people were extremely successful on App Engine, you heard Snapchat today, but there's many other examples. People really love App Engine because they can walk away from an application after they deployed it. And really, the way we say it, your only maintenance action for years is to renew your credit card. Right? That's really all you have to do. And there's incredible value in that. But even the biggest users of App Engine said, hey, look, I have this other piece on here. And it's not realistic to rewrite it, or I don't want to rewrite it, or it's actually great as it is, and I need to be able to just run it. Right? And for that, you need VMs so they can wrap them around. And our goal really is to say, look, pick the parts that you like most, right? Implement the components the way you sort of see fit, and then fit things together into a low effort, high performance, easy to maintain sort of system. And so it's really not an either or. And I think, so that's that. And we set out certainly with a vision of having something that's very high level, very easy to use, and very sort of low touch once you're done, very productive. And actually, if you asked me to bet, I would say 10 years from now, that is going to be the main way of how you actually use the cloud. Because if you can fit into that pattern, it's so useful, right? I mean, it's so low cost because you don't have to touch anything that's really a big win. But you got to cover the entire spectrum, and there's a lot between now and 10 years from now that's going to change. So this is an iffy bet even for me to make.
Okay. So when you run and manage the world's largest data centers, and you're hosting millions of applications and that application data, security has to be just at the top of your mind. And why should developers trust their data to the cloud?
So I think there's two answers. One is because we're probably going to do a better job than you would do yourself, because security is hard, and there's always all kinds of ways to screw up. And we have a great team. The second one is that there used to be this conception that IT needs security, right? That's where your standards are high, and consumers, they will deal with something that's insecure. But that's not really true, right? With consumers having moved much more of their personal data in the cloud, they set the very high standards. They have very high expectations. And so for us, as a consumer cloud provider, a security incident would be extremely expensive. And so we're actually spending hundreds of people, right, on security, a very, very good security team, to really try and make that extremely unlikely. And even on the consumer side, you have security features like one-time passwords that are ahead of many enterprise products today. Or our HTTPS for years now has used elliptic curve cryptography, which makes it much, much more secure against intruders, even if you get the master key at some point. You still cannot decrypt recorded sessions. So we've worked really hard on that, and I think if you look at that as a developer, do you want to take advantage of that, or do you want to try your own luck? I think you're going to be better off at doing it this way. And then in the cloud, we have the extra advantage that if you wish, you can go encrypt your data with your own key, where not even we have access to it. So you get the infrastructure that's already very secure against sort of the common mistakes. And then on top of that, you have your own extra layer of security under control. And so that's really a pretty good place versus hosting yourself is really, I think, a bad proposition.
So you could get the best of both worlds that way.
Exactly, right? You can layer on top, you bring your own security, but you really benefit from having, from all the work that we've already done. And in the long term, like people ask about, oh, what about security in the cloud, compliance in the cloud? That's just as much of the success as technical features, right? So if the cloud really 10 years from now is a major factor sort of in everything IT, then very clearly it needs to be the best security place and the best compliance place, just as it is the best technical place and the best economical place, right? These things need to come together. You can't really leave them out. So almost by definition, right, our security will be very good because it has to be.
Yeah, okay. So I'd like to move in a little bit to sort of innovation at scale. And Jeff, since we have you here, you've been involved in all the large-scale distributed systems at Google. And I wonder if you could sort of share some of the challenges you've sort of witnessed and had to deal with and program around that really only happen at that very large scale. So things that you wouldn't see if you have an aisle of servers in a data center, but something you see when you have data centers full of computers, warehouse-scale machines, many data centers across the world, 15 years of sort of running software on there.
Battle scars.
Yeah, tell us your battle, show us your battle scars.
I think there's a lot of lessons we've learned over time. And from the very early days of Google, we had hardware that was kind of very consumer-oriented hardware. It didn't have a lot of sort of reliability features built into the hardware that you might like ECC memory or even parity for our earliest machines. And so if you sort a terabyte of memory, a terabyte of data with a machine's without parity, it ends up mostly sorted. And you sort it again, it's mostly sorted some other way. So I think, from those early days, to work around that, we built sort of a software checksumming library that is sort of in constant use in all pieces of our infrastructure, just to make things more robust to that kind of very low-level hardware error. Now, modern machines have ECC errors, but sometimes switch buffers don't necessarily have ECC, and so you can get corruption even in network transit, and so these kinds of things are really good for protecting against that. And then I think when you're pushing the boundaries of scale, like you're running systems that are thousands or perhaps 10,000 machines, you see failure modes that are really rare but are very perplexing and annoying that you wouldn't necessarily see if you're running a 100-machine system. So a good example is if a whole rack switch goes bad, that's a pretty rare event, but all of a sudden, you lose 40 machines or 80 machines off your network. But even more nasty than that is like a switch that kind of is kind of working. So it drops half the packets coming through it. And all
only
of a sudden,
in one direction.
Yeah, or only in one direction.
Right.
And that's actually tricky because things like health checking and so on that are designed to see if something's alive, actually work. Like it is alive, it's just incredibly slow and you can't actually communicate effectively with the machine. So, these are the kinds of problems that you see running at scale. And one of the things that has happened is you recognize these sorts of problems and then you build infrastructure to sort of, in software, deal with these kinds of failures automatically. And so, some of the things that we've built into MapReduce are designed to be robust to not just a particular kind of failure, but lots of kinds of failures, even ones we can't imagine right now because the software techniques are just effective at dealing with when things aren't working right, no matter exactly how they aren't working right.
Yeah, okay. So Urs, you co-authored a book, it's called Data Center as a Computer, An Introduction to the Design of Warehouse Scale Machines. And in there you talk about this sort of software tolerance. If we get to the point where we can design some of our own hardware and build better switches. Tell us why we can't just build better hardware so Jeff doesn't have to work so hard.
We can, and we do, but Jeff still has to work hard. No, the problem is that really scale kind of in the end gets you, even if you try to avoid it, because even if you had an incredibly good piece of hardware, there's no manufacturer in the world that can make 100,000 of them and have them work 3 years without things failing. And so once you accept that you will have failure really as part of every day, then whether something fails 3 times more often or not is actually not your problem. The problem is that there's failures that you have to recognize and isolate and sort of automatically deal with. And so I think we came to peace with that a long time ago, because you really realize, okay, even if I could do it better by a factor of 10, and I don't see any vendor who does it better by a factor of 10, but even if I did it, basically my software effort is still the same, because failures would still happen. And to some extent, actually more frequent failures are the ones that you handle really well, because those are the really well-tested kind of things. So to some extent, there is really not an advantage of making them more rare. And so generally, we pick the right point. So today, we do have ECC memory, because memory errors actually are, at today's lithography, are even more common than they used to be. So you absolutely want to have it. But still, do we actually have memory errors that even ECC, 2-bit ECC correction does not detect? And the answer is yes. Right? At scale, you're going to see that. And I haven't done the computation recently, but I'm sure we see it at least every week, probably every day, just based on the amount of RAM that we do have.
And the solar flares. Actually.
Exactly, right? alpha particles, and so on and so on. And so you have to go deal with it, right? And have enough resilience so that you can actually still move on.
So being on the way I sort of read this and summarize it is, so being on the cloud platform sort of insulates me from solar flares.
Among other things.
Among other things.
Hopefully, yes.
Yeah.
Yes, hopefully, yes. And we really hope that we can expose some of these things that we learned as tools that make it easier for all of you to build applications and not actually have to understand how to deal with failure, because as long as you follow these simple rules, you will be fine, right? That's kind of the ideal situation. Today, we have realized that in App Engine and on the VM side, to a smaller extent, we've realized it with a VM migration, where we're able to move you away from something that we see coming, and you don't know this even happened, but we can do a lot more in that area.
Okay. So Jeff, when you were building the first iterations of these distributed systems 14 and a half years ago, did you realize when you were sort of trying to make the engineering trade-offs and dealing with failures, providing availability for the systems and consistency, did you realize at the time that was essentially those 3 components, the CAP theorem, consistency, availability, and partitioning, that were really underlying the engineering decisions?
I mean, I think...
So, just to interrupt, I think it's called Brewer's theorem. At least that's how I like to call it.
Really? I always call it the CAP theorem.
No, it's Brewer's theorem.
Sure?
I think I know this
I
one.
think it's too much about cats, I think.
No, CAP.
I think I know this one.
All right.
Can I join you?
Yeah.
Everyone, please welcome
Eric.
Eric Brewer.
What a surprise.
Nice to see you again.
Eric, thank you for joining us. So you noticed that we had a 3-person couch, so obviously we needed a third guest.
Saw that coming.
If you don't know Eric, he devised the CAP theorem, or Brewer's theorem. We'll let him answer that question in a moment. He's a professor at UC Berkeley of computer science, pioneer really in building large-scale systems, built the first really useful cluster for web infrastructure. And can you tell us, do you prefer CAP theorem or Brewer's theorem?
Actually, I prefer CAP theorem because it sounds bad coming from me to call Brewer's theorem.
Okay.
So you can call it whatever you like, but I'm always going to call it CAP theorem.
I'll call it Brewer's theorem.
That's all right. I don't mind.
Can you maybe tell us a little bit about CAP theorem? I think sometimes it's explained sort of incorrectly as a 2 out of 3 choice.
Well, I think in 2000, or really when I first thought of it was about 1998, it was a 2 out of 3 choice in the sense that we were in an era where everyone wanted asset properties and wanted us to build literally cross-national systems that had both availability and consistency. And I realized we weren't able to do it, but also that we were regularly choosing availability over consistency. And, but people didn't accept that that was the choice that I had to make. So they were actually very reticent to say that's an okay choice. And so the CAP theorem in some sense was to give everyone, myself included, permission to choose availability, right? And now that's what happened. People like Jeff chose availability for BigTable, and many others have as well. And I think it's because the internet's the first time we had a kind of 24/7 service, except maybe the phone system, which isn't really a data system, it's a communication system, where you actually had both data and availability that you wanted to get. And so we actually start making some difficult choices, which we still make, actually.
Okay. So you've, in addition to CAP theory, you've also looked at sort of the origins of SQL and NoSQL databases. And on the cloud platform, you can get a managed SQL service, a managed NoSQL service, but you can also sort of run your own. If you do VMs, you can spin up Cassandra and have your own flavor of a large NoSQL system. How should developers sort of think about those trade-offs and how do they select one over the other?
I actually try not to choose, even though I've just told you that you have to choose. You only have to choose if you are going to have partitions, and only during the small amount of time where you have partitions, right? The rest of the time you can actually mix them much more gracefully. And I would say we've already built systems, and certainly talked about some like Spanner that Jeff worked on, where you can set it in a more of a consistent setting or more of an availability setting, and you can make those choices on a relatively fine grain. If you know you want partitions, like you're doing mobile phones or disconnected operation, and you really are going to have truly concurrent operations on both sides of a partition, then you really have to plan around that and think about your merging. Otherwise, I think you can be a bit more graceful about it. At least that's the modern answer, I would say. Okay.
So you can have sort of all 3 legs of the stool, but just not all at the same time all the time.
You have to play with them a bit more gracefully.
Okay. So Jeff, if you've been building sort of many generations of these storage systems, and there's maybe you can talk about sort of the problems you were working on when you developed a BigTable and MapReduce. What were sort of the fundamental BigTable or sort of big data problems that?
So MapReduce sort of originated when my colleague Sanjay Gamawat and I were actually working on rewriting the core indexing system for web search at Google. And the pipeline at that time goes from a bunch of raw pages on disk that our crawler has collected, sitting in a bunch of files. And you have a bunch of stages that are trying to sort of transform it and do things like find duplicates and choose which one of the duplicates you want to choose because it has a prettier URL, compute PageRank, decide which pages we're going to put in the index, what language they're all in. So there's all these little phases that conceptually are doing pretty simple things. But the code had gotten really complicated because in each of those phases, we'd kind of rolled our own parallelism for that phase. We say, well, this one runs pretty fast, so we need to use a couple hundred machines. This one's slow, so 1,000 machines would be better. And each one of them had its own checkpointing mechanism and recovery mechanism for that to deal with failures, because when you're running on that many machines, you have failures. And so what got lost in there was actually the fact that all these operations were relatively simple and straightforward, and they were obscured by all this sort of nasty support code. And so Sanjay and I kind of started squinting at each of the phases and looking for abstractions that we felt could represent all the simple computations we were trying to do in a way that we could then hide all the complexity of dealing with failures and automatically parallelizing across an appropriate number of machines and dealing with slow machines in a library. And so MapReduce is kind of what we came up with. We have both have backgrounds in looking at different kinds of programming languages, and the functional programming language paradigm is a pretty useful one. And so MapReduce kind of builds at least loosely on that. And so we realized that all the phases in the indexing system could be represented in this abstraction, and then we could work hard on making that one library perform really well. So that's kind of the origin of MapReduce.
Okay.
And the origin of BigTable is kind of similar in that we wanted to have an incrementally updating system for all of our indexing systems. So we wanted to have a row of data for every page we know about. and then have different columns that are being asynchronously updated. So the crawler would go off and fetch contents and then write the actual current contents into one of the cells. And then there'd be other asynchronous processes updating things like what language we think that page is. All the different phases we used to run in a pipeline would now run kind of asynchronously. And then we'd always have the current state of this page by just looking at that row.
Okay.
And we needed to scale that out to a very large number of machines to deal with all the pages that we wanted to represent. So.
Okay. And then how did that lead then to Spanner? What subsequent problems were you solving that BigTable didn't address?
So the first version of BigTable essentially ran within one cluster, within a single data center. And then over time, we added some support for sort of eventual consistency to have more interactive services where you wanted to keep a bunch of geographically distributed versions of the data in sync. But that was kind of somewhat unsatisfying because you actually want all of the things that
Yep.
you mentioned. You want consistency and availability. And it's actually kind of a pain for developers to deal with having 12 BigTable replicas of their data scattered around the world. And so what Spanner solves that BigTable didn't really do is the problem of geographic distribution of data across wide areas potentially. And also some flexibility in allowing users to say, well, this particular data, I want to keep 2 copies in Europe and 3 in the US, and I don't really care where I keep them. That's just roughly where I want them. Okay. And that gives the underlying system freedom to move data around in response to changing patterns of demand and load and disk availability in our European data centers. And also, Spanner allows users of the system to select the appropriate consistency trade-offs. For some operations, you want a strongly consistent view, and you may pay for it in availability. Other ones, if I'm marking an email message read or something, it's probably fine to have an inconsistent view of that data. What's the worst that can happen? And so I think allowing users to pick that trade-off appropriately for the different pieces of their application is one important thing Spanner allows you to do.
Okay. So Eric, you joined Google about 2.5 years ago.
Yes.
And you're currently on sabbatical from UC Berkeley. And you've had a chance to look at innovation sort of in the academic setting, the commercial setting, and you've seen it sort of firsthand inside of Google. How would you compare the way innovation happens? Is the pace different? What does it feel like to be inside of Google, and how does it compare?
Well, when I started in this area, which is almost 20 years ago, we had a cluster of 4 machines. You could put it on a desk, and that was actually enough to make progress on cluster computing. Right? You could actually solve problems that were new with 4 machines. And now we're at the state where you really need many, 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 many more machines than that. And so I kind of feel like Google's the place to be to have the problems that I want to solve. Right? They just aren't anywhere else because of the scale and because really of the goals. It's an ambitious place to be. And I think I get a lot of challenge out of that and great enjoyment.
And do you think, is the pace different of innovation? Is it faster at Google?
Yeah, well, I mean, it's faster in several dimensions. It's faster because you have vastly more people. It's also faster, I think, because there is an urgency, right? There's not much urgency to cloud computing in 1995. I remember we went from 10 machines to 100. That was a big deal, right? Like, woo, 100 machines.
Factor of 10.
Yeah, it was a factor of 10, and the things broke, and we had to fix stuff. And so, but it's definitely not the breadth of stuff going on, and also, I think, not really the same ambition. The time is more ambitious now, and that's great for everybody.
So it's harder problems and just bigger scale, really, that
Absolutely.
that drives this.
And actually, Fred, if I can, having been in academia myself, I think one of the big differences really that today I think academia struggles with is that you may have the ideas, but you don't have a good way to test them, right? And not just because you lack the infrastructure, but you also need real-world applications to actually
That's right.
test
You need users and data.
your thesis, right?
Yeah.
Whether it really works, right? And one of the great things at Google is that we're in a pretty good place already because we been working on it for 10 years, so the standard is relatively high. We have great people, and we have great problems to solve. And together, that really kind of gets an acceleration sort of factor. And my favorite quote actually from the last half year or so, for those of you, just a short digression into networking, Van Jacobson, if you know TCP, you know Van Jacobson. So he's at Google. He joined us, last spring or so, and I talked to him in the summer, and he said, I didn't expect that, but in the last 4 months, I've gotten done more than I have in the past 5 years. And I said, why? And the answer was, I can actually test an idea, and I can test it very quickly, and then the next day, I know I was wrong, but I have a better idea, and so I can actually.
Yeah.
And before this took me years, right, to get to that point, and that's really, I think, one of the big opportunities I have, and that's why I said before, 10 years from now, really we're not going to live in the same world, right? Things will profoundly change because we can discover along the way the things that we do right and the things that we do wrong, and then think of better ways or more innovative ways to do them wrong, right? And then, but over time, right, we get them less and less wrong.
Yeah. So talking about sort of that pace of innovation in the future, I see, Jeff, you wore your Google Brain shirt. So I wanted
cerebellum is folded, though.
I wanted to ask about that. You wrote a blog post in I think it was 2012, and you described what I'll just call a very large cat detector. But there's a lot more behind it. I wonder if you could talk a little bit about the project, what you did in 2012, and then maybe we can talk a little bit about what's happened since then and what the benefits to other Google products have been.
Sure. So the last couple of years I've been working on, I switched gears a little and have started to look into very large-scale machine learning systems, and in particular, systems for training very large neural nets and then using them for a variety of problems. This project started because Andrew Ng is a Stanford faculty member with expertise in this sort of field of machine learning, and was spending a couple days a week at Google, and he and I bumped into each other in a kitchen, and he said, oh yeah, I'm thinking of figuring out how to use neural nets for things, and I'm like, oh, that sounds like fun. I'd actually done an undergrad thesis on parallel training of neural nets a very long time ago, actually. So he kind of said that at small scales, these kinds of approaches were showing pretty promising results in perceptual tasks, things like computer vision and speech recognition. And so I said, wow, that sounds like if we just made them bigger, they'd get even better. And so he and I and a few other people started to form a little project around this of can we build systems that allow us to train very large neural networks to accomplish interesting things. And so one of the first experiments we did was to do what's called unsupervised learning, where you don't have sort of the desired output of the model. You just have a bunch of raw data, and you want the model to kind of capture regularities and interesting patterns that it observes. So the experiment we did was we took 10 million YouTube videos, one of the benefits of having lots of data lying around, and we took one frame from each one of them, so it's kind of a random sampling of video frames. And we put it through a model where we essentially just tried to learn representations that were good at reconstructing what the individual images were. And so the training was done on 16,000 cores, and that's one of the benefits of having these large-scale cloud platforms is that we can do those experiments and get results more quickly. So getting back to Van's point of being able to get results on your experiment to figure out what the next thing is that you want to do, being able to run that on 16,000 cores instead of 1,000 is not necessarily as efficient as doing it on 1,000 in terms of actual dollars, but it lets us get our results more quickly, and so we're more effective. So anyway, we trained this model in a completely unsupervised manner, and then we looked around at what the highest layers in this model, so it's like a deep 10-layer neural net, and at the lowest layer, the neurons learn to be responsive to very primitive things like edges at different orientations. And then as you go up, the neurons get a little more complicated, so they'll learn like corners or things like that. As you get a little farther up, you'll get like pieces of chair legs or things like that. And so we looked at the top layer, at the very top of this model. There's 60,000 neurons. And then we had a test data set that was, it's YouTube. So we said, well, there's got to be cats. So we took a test data set that was half cats and half not. And we knew those. And we looked around for a neuron that was most sensitive to whether or not the image contained a cat. And if you can just skip ahead. So we looked, and we found a neuron that was actually pretty responsive. So these were the images that caused that particular neuron to get the most excited. And you see that they're mostly cats. There's one Starbucks mug there, but mostly cats. And I don't know, if you can see this is actually the representation of the optimal stimulus, the thing that would cause that neuron to get the most excited. And that's actually a cat. It's pretty cool. We call it average cat. So
the house cat.
by just training on a lot of data, this model has essentially invented the concept of a cat without ever being told what a cat is. And that's, I think, a pretty fundamental thing. We looked around at other neurons and found ones that were receptive to faces and backs of people and sort of concepts you would expect these models to represent from just looking at a whole bunch of images.
I think we have another slide. Let's look at this next one here.
Yeah. So then we shifted gears a bit and realized that although this unsupervised learning was incredibly cool, there's actually more applied uses you can make if you have a large supervised data set. So you have a bunch of images and you have a bunch of labels. So an image of a cheetah and the label is cheetah, and a garbage truck, garbage truck. If you can directly train on that objective where you want to give it an image and then have it tell you what it is, supervised training is actually pretty effective. And so again, once we've done a little bit of supervised training, we then looked at what are the optimal stimuli for a few of the neurons at the top layer of this model. And you see that some of them are pretty good at succinctly finding things that we would, as humans, know what they are, like yellow flowers or wine bottles or balsamic vinegar, or pizza at the bottom. And some are kind of a little more abstract. They aren't a single sort of succinct category, but they're things like very textured, spotty objects. So I think that's kind of an indication of what's going on in these models, and it's interesting.
Okay. So 16,000 cores, probably 1,000 machines or so.
Yep.
How many to detect a cat? So how many cores would we need to represent the brain of a cat?
Well, I think those kinds of comparisons are hard because we I think, have a pretty good handle on how to do training for sort of categorization tasks. But the brain of a cat actually is much more complex and has a lot of sort of mechanisms in it that we don't understand quite as well from a machine learning standpoint, how to do sort of feedback and control. But from a perceptual viewpoint, I think we're getting a handle on how to train interesting systems to do perceptual tasks pretty well.
Okay.
We actually have a fair number of those perceptual tasks at Google. Some of them are very general things like this general object recognition, and some are more fine-grained. So the Street View team, if you can click to the next thing, wanted to be able to find text in arbitrary street scenes. And so with a little bit of labeled data, we had some people draw bounding boxes around text in some scenes. You can actually see that this model does a pretty good job of finding text in these scenes, which is kind of the precursor to then doing OCR of the world. Maybe I have one more example there. It's just another street scene. But it's a pretty challenging problem because you see like there's all kinds of things like logos and different font sizes, different fonts, different colors. But this model is actually able to do this very effectively and is doing it from raw pixels. So you just feed in raw images and it is able to sort of give you this nice heat map of where text might be. And we have other models that find street signs or other kinds of interesting things in these data sets.
And have there been benefits to other Google projects from Google Brain? Like you mentioned voice recognition, is that being used?
Yeah, so we've been working with a whole sort of a growing array of different teams. We've had some very initial close collaborations with different teams. So the speech team was definitely one of the early clients we worked closely with to use our distributed training system for problems they had. In particular, they wanted to build and train very effective acoustic models for speech recognition. So that's kind of the first part of speech recognition where you go from a quarter second of raw waveforms of speech to predicting what is kind of the sound being uttered in the middle 10 milliseconds. Is it a ba or a f or a s, that kind of thing. And then you kind of stitch it together with a language model to actually figure out what the utterance is. And so working with them, we were able to train a pretty big acoustic model that was actually much more effective than the previous kind of model they were using for this. And the word error rate for English recognition dropped by 30%.
Wow.
Which is sort of a really huge drop. Like this is kind of unheard of.
Unprecedented drop.
Yeah. And 30% drop goes from like not quite usable to actually quite usable for a variety of tasks. And we're continuing to push on making the models bigger and better. And then a whole bunch of other teams kind of came to us after they saw that success on speech and on some of the image tasks. And now we have about 30 or 40 teams within Google applying these models to all kinds of different problems.
Okay. So the neural networks that you're sort of working with, the basic form thereof, they've been around since the 80s. Why is it that we're making progress now?
So I think a few things. One is, as you say, the basic ideas have been around for about 20 years. 20 years ago, there wasn't enough computational power to train very large and in particular very deep networks. So people were playing around with neural nets that had maybe 2 or 3 layers of abstraction in them and on fairly small data sets. So I think the big difference is we now have enough computational power and big enough data sets to really train very large models and have enough computational power that we can do that in a reasonable amount of time. We have kind of what we call a patience threshold of 4 or 5 days we're willing to wait for a model to train completely from scratch, and maybe a day if we're like really experimenting quickly. And so the reason we use lots and lots of machines is because we want to train the biggest model we possibly can in that patience threshold. And if we're able to train a bigger model because we can parallelize things better or use more machines, that's just gravy because we can then train more effective models on larger data sets and so on.
Okay. So I'd like to sort of step it back into the data center world. And so we've just talked about this neural network with 16,000 cores. That in sort of Google scale is probably a small scale system. When we talk to lower level storage systems, and they're much larger. How does your technical infrastructure team sort of deliver the network so that all these machines can talk together, both globally and sort of within the data center?
Yeah, it's definitely an interesting problem, and one of the nice things is that it's kind of like having a child, right? Doesn't come with a manual, but fortunately they don't actually, like they grow up slowly, and so you have some time to catch up with their demands, and that's kind of been us with networking or compute or storage. If we had the problem from sort of day one, then we would have been pretty overwhelmed. And so networking is actually something that's become very important in the last 10 or so years, and we've started to do a lot of work because we got to the place where, just like with compute or with software systems, we couldn't buy what we needed. There wasn't really a vendor. So it wasn't a question of, should we build or buy because which one is cheaper, but really there is nothing out there that you can buy, right? So you have to actually build it. And one of the biggest sort of leaps we made recently is to convert our, actually let me back up 1 second. So we started building networks, obviously, right? Both inside the cluster and between all the data centers. And so we've been owning dark fiber and lighting our own optics, et cetera, for a long time, because at scale, you kind of need to do that, both for capacity and price reasons. But one of the biggest steps that we made recently was to convert much of our external backbone, so this is the backbone that connects the different data centers together, to run not on traditional networking protocols like BGP and OSPF and LSPs and all these things, but MPLS, but on OpenFlow, which is actually kind of very cluster-ish kind of idea of how to control networking, where basically takes the same idea from cluster computing, where you say, gee, the individual node shouldn't really make decisions. Let's have a manager, like the nodes are dumb. They basically, they're just a pool of nodes, and we tell them what to do. Rather than them trying to communicate and figure out what to do. So in networking, once you have a certain scale, you actually want the elements, the routers, the switches to be relatively dumb because they don't really understand what's going on sort of worldwide. And OpenFlow, or software-defined networking in general, really brings that world much closer to the software world, right? So now we have a global network that we can control much better and at a much higher level, sort of more at the application level, if you want, rather than sort of at the network level. So we can worry about, hey, here's 2 Gmail cells that are talking to each other, and not about here's port 1, 2, 3, 4, and some QoS class and some IP ranges and things that are just brittle, right? And so that has helped us a lot in really pushing the envelope in terms of how fast we can grow and how well we can control it. And one of the biggest advantages, and that's really what we've seen, I think since the 90s on the cluster side, is that once you move something to be sort of more software controlled, you can simulate it. And simulation means you can do better testing. So one of the big reasons why we're actually able to switch our global backbone from traditional to a completely new stack in about 15 months was that really we couldn't do that testing it on the real hardware in the real world, right? That would be pretty risky. But we were able to build our global network sort of in software as an emulation, and so we could play through all kinds of disaster scenarios. What happens if this thing goes down? What if this thing goes partially down, right? What if you'll lose this line, right? Does the software react correctly, et cetera? And so if you can do the software testing, really the whole integration, unit and integration testing, then you have much higher confidence that when you actually try it out, it will really work, right? And if it doesn't work, you can explain it in a much better way. And once you've figured it out, you can add it to regression test suite, and it won't happen again, right? You won't break it again with a new software release. So in networking, I would say that really in the last 10 years has probably been the biggest change, that now networks are becoming much more cloud friendly, if you want, or cluster friendly, because we can start to program just like we could program the nodes in the data center or the storage elements. And you can take the big picture, sort of how do you want to orchestrate things, and sort of automatically translate it down into what the network elements need to do. And your operator doesn't need to do that anymore. And that really is a huge change. And we're still discovering new opportunities of how that really sort of percolates through the entire stack. And you say, oh, over here, like I used to do it this way, but now there isn't really a reason to do it this way, because now I can do it the easy way, because the network now actually understands what I want to do.
Okay, so we've heard a lot of sort of innovation and research. Jeff, I wonder if you could talk about sort of Google's philosophy between research and engineering. How does Google make the trade-offs between the two? How do you decide which team you work on?
Yeah, I mean, I think one of the things that I really like about Google is that we have this very continuous, not hard boundary between research and engineering. So I'm in engineering, but I work on kind of longer term problems sometimes and work on shorter term things some of the time. And really, you're not a researcher or an engineer. You're working on problems that fall on different parts of this continuum. And the same person might move back and forth on this as they work on some very long term thing and then gradually get it closer to being ready to deploy to real users or whatever. Then you become a little bit more of an engineering hat. I think that's a really valuable thing. So, on our team, we have a bunch of people who are a little bit more on the research end of the spectrum, a bunch of people who are a little bit more on the engineering end of the spectrum, and collectively, we can do things with kind of complementary skill sets. So there's a bunch of people with a lot of machine learning expertise on the current team I'm working on, and a bunch of people with kind of large-scale distributed systems things. And collectively, we're doing things that none of us could do individually because we just don't have the whole set of skills in one person. And I think that's really fun because you learn a lot about that. You learn about how what are the trade-offs in doing machine learning algorithms at scale. And I think that's a really valuable thing to keep working on interesting problems and learning a lot as you.
Okay.
And we've done that very deliberately, actually, because, and you see that today in cloud, but you saw that in search 10 years ago. When you have a problem that is so early stage, basically, and you can see the ramp that really is going to change by orders of magnitude, you can't sort of incrementally engineer the product to a better state. I mean, yes, you do that, of course you have to, but at the same time, you really have to fundamentally rethink things all the time in order to have a chance of actually keeping up and hopefully, even, getting ahead versus the problem. And so research versus engineering, it's almost, not sensible to ask the question, right? Like, how are they different? They're really kind of different facets of the same thing. And if you don't really tightly couple that, you're going to have research that is no longer grounded in reality, or you're going to have people who are too much grounded in reality, are just making today's problem better rather than recognizing that tomorrow's problem is actually very, very different and requires something new that is a departure from what has served you well in the past, right? And so we're trying to really blend that all the time and give people some freedom to do crazy things, because what looks crazy today might actually look obvious tomorrow, and so you have to kind of balance that.
Actually, a good example that came up today, which is the demo that was given this morning about doing live migration of a video player, is a demo I gave internally about a year ago. And that idea was in academia, I think, in 2003. But to get it right in Google, it took a while, and to actually convince people with something we want to bet on it. This is how we're going to run our clusters. That actually takes internal consensus and solving the whole problem, which you don't solve in academia, right? That's a big problem. It has to work for all the cases, and then you actually then get people to take that actually to product, which is now seen.
Okay. So you talked about building systems. When you built the Inktomi search engine, you of course sort of had to get your own gear and get your own cage in a data center, even shared one next to Google.
We were neighbors, yes.
Oh yeah, I visited that cage.
They sent heat my way.
Yeah, yours look much cleaner than ours.
But for the record, modern Google clusters look more like Inktomi clusters.
It's true, it's true. We no longer bungee cord our racks to the pipes.
That's more than 10 years ago.
Yes.
Yes. Would you, if you were doing it over again today, would you build Inktomi on the Google Cloud Platform?
Yes, I think that part's the easy part of the question, right? Which is, any startup shouldn't be investing in their own infrastructure, right? It's not the core competence, right? It's not fundamental to what you want to do. I think the harder question, which I think you can uniquely answer now, is when Inktomi got to a size where it could afford to build its own data center and have its own machines, should it or should it not? That's the harder question. And before today, the answer would have been Inktomi should have, because there would be significant cost savings to do so. But if Google's willing to provide virtual hardware on the same Moore's Law cost curve as the real hardware, then there's no reason to switch. And that's actually comforting, because it's a big pain to switch. So that's new, actually, new today.
So, Jeff, maybe not quite a final question, but what problems are you working on today? Is it still Google Brain? Is it an extension thereof? What are sort of the future problems that you're trying to solve now?
Right, I mean, I think one of the things that these neural nets are able to do is they're able to take very raw forms of data and then automatically build interesting high-level abstractions of that data and give you things that you can learn from that data automatically. And so unlike a lot of other machine learning techniques where you kind of hand engineer features you think are predictive of something you ultimately care about, these systems can build that sort of automatic combination of interesting features and discover what is actually interesting in your data automatically. So I think that probably is a very, how can we sort of package that up and make that easier to use has been a question we've been wrestling with within our group as more teams within Google try to use this for their own problems.
Okay.
We're making some progress on that, I think.
Eric, what problems are you trying to solve right now for Google?
That's the funny thing is, I can't talk about it. Right, in general. I've been here 2.5 years, and Urs mentioned before that we kind of, about 2 years ago, started making transitions to what we want to build, a kind of joint infrastructure for internal use and external use. And that's kind of what I've been working on for those 2 years. You can kind of see glimpses of it, but frankly, the best is still to come.
Okay. Urs, maybe final thoughts for today?
Sure. I think Eric is trying to say we're solving problems that you don't know you had. No, but actually, I think Eric's pointing to something that's pretty profound. I mean, if we like clearly where we are today is very cool. And if you had asked me 10 years ago, like could we ever get to this kind of scale and have it work this way and it actually being available to really, everyone, sort of at this scale, I would have said, no, that's probably unlikely, right? And so to some extent, really, it's incredibly cool where we are, right? It's amazing when I look at a picture like this, the fact that, we can stamp these out and they work this well and they're cost effective. And I mean, it's really, I'm sometimes surprised myself, right? But in the grand scheme of things, I think we shouldn't kid ourselves about having solved the problem. We haven't solved the problem at all, right? In fact, we're kind of, 2% in or so. And so I think the most amazing part to me is that I'm really confident that if we look back 10 or even 5 years from now to where we are today, and the things that we're proud of, right? Whether that's recognizing cats or handling petabytes or something like that, we're going to really be kind of embarrassed because it's so lame, right? And 5 years or 10 years from now, it will really be obvious how lame it was, even though it seems amazing today. Because we're so early in the cycle, and we're just having, literally in the last 5 years, the different elements come together, right? Having data, like actually solving the whole availability, partitioning, consistency, like in Spanner, for example, is a much better solution than we had earlier. MapReduce, we're not actually using MapReduce anymore for new code, right? We have a new thing that's called Flume, and actually is an even more elegant way of expressing these things. But just in the last 5 years, we've had sort of the hardware and software pieces come together that actually are a good starting point where you can go off into a Google Brain within a pretty short amount of time. But if you take that ability and then really the innovation that happens everywhere sort of based on that, I think we'll really see an acceleration or an accelerated pace of discovery and innovation over the next 5-10 years, right? And so we all underestimate how fast that really will be. And we kind of, realize that, okay, 5 years ago we didn't have, smartphones basically or whatever. But, 5 years from now, the smartphones, they're kind of just going to be, faster and cheaper than they are today. No, they're not, right? They're actually going to be profoundly different as 5 years ago, the what was it, the T-Mobile G1 was, compared to the Nexus 5, right? These are not the same thing. And so the same thing is going to be true for cloud. So, when we sit here 5 years from now or 10 years from now, I think we'll have some pained smile if you show us videos of this conversation today or of our keynote this morning and say, yeah, I guess given the time this was sort of cool, but today really, that's what you were proud of. So to me, that's actually the most exciting part about all of this, right? We really are just at the beginning. Only 1% of the world is in the cloud. I think only 1% of the cloud's problems are solved, really. But I think 5-10 years from now, we're going to be well into the double digit on both of these sides, and it's going to be a very exciting time, for me as a computer scientist, and I think for everyone sort of as a developer, to be part of this, right? This could easily be the time where, decades from now, you tell your grandchildren or whatever, yeah, I remember, this was a time when we went from sort of Stone Age to pretty modern in computing, in really software systems, and I was there, right? And now I realize how important that was. So I hope that 5 years from now you all agree with me on that, but I really think we're at the beginning of something pretty big and something that I'm more excited about than I've been in a long time.
Great, thank you for that.